You should be absolutely clear at this point that a terminal is just a dumb device for displaying text characters on the screen and for sending text characters from a keyboard to a program that wishes to read them. Without programs reading from a terminal and writing to it, terminals are pointless. What we call a shell in Unix is a program which reads from a terminal and then interprets what the user entered as a command and executes that command. Effectively, a shell is an interpreter for a programming language. It's just that the expectation with a shell is that there's a user typing the lines of code one by one, and each time they enter a line of code, the shell then immediately executes it. So we can say a shell is like an interactive programming language. The user types a command, and then the shell immediately executes that command. For many years, the most widely used shell on Unix systems was known just as sh for shell, but more formally it was known as the Bourne shell because it was created by a guy named Stephen Bourne. For the most part, all the other shells that have been widely used at one point or another that I list here are really just variations on this original Bourne shell. Most of them take the core of the Bourne shell and just extend it with additional features. Perhaps the one exception here is the C shell, which changes a few things about the syntax of the original Bourne shell, as well as adding additional features. The Korn shell, for example, so-called because it was created by a guy named David Korn, was created a few years after the Bourne shell, and it mostly adds things rather than changing anything about the core shell syntax and features. Of all the shells listed here, the one you need to become most familiar with, and the one we're going to focus on, is Bash, aka the Born Again shell. Bash was created in the late 80s by the GNU project, and so it got adapted as effectively the default shell in Linux systems. So in fact, most of the time when you open up a terminal window on a Linux system, it will most likely by default have the Bash shell running in it. Again, the Bash shell is pretty much just an extension of the original Bourne shell. I don't believe there's actually anything that they changed about the original shell, they just added more features. So say I boot up my Ubuntu system and the X Windows server then starts, and finally my whole graphical desktop there is loaded and ready to go. If I then open the terminal program, I'll get this terminal emulator window, and in it is running the Bash shell, because that's the default on Ubuntu systems. And as you see here, what I'm presented with is first a prompt, and the prompt displays my username followed by the name of the system, which here just happens to be Ubuntu, I suppose. That's then followed by a colon, after which is listed the path of the current working directory of the shell. Recall that every process in Unix has associated with it a current working directory, or sometimes called the process working directory. In this case, it is listed as a tilde, because in the Bash syntax and shell syntax, tilde is used as a special signifier, as a special shorthand for my home directory. So really what should be printed here is /home/Brian, and this is just shorthand. We'll talk more about the special meaning of tilde a bit later. In any case, so after the listing of the current working directory, there's a $, which simply denotes the end of the prompt. And then after the prompt, there's a space and my text cursor, where if I start typing, that's where my text is going to start appearing. Because when the shell is waiting for you to enter command, it puts the terminal into echoing mode. So now I can type my command, and as I type it, the characters will appear in the terminal, and once I hit enter, the shell usually interprets the new line character as the end of a command, and so it will then interpret that command and execute it. Before getting into the details of Bash syntax and semantics, I'll just remark here that shell languages have what I like to call a command-based syntax and semantics, in contrast to the expression-based syntax and semantics we've seen in languages like JavaScript and Python. This stems from a very different design goal. Shells are mainly about not writing a whole bunch of code that runs within the shell, but writing code that simply launches other programs. So while it's perfectly possible in, say, Python to launch other programs, it's not made especially convenient because Python is mainly about writing code to run directly in the Python interpreter, not to run as separate processes, whereas in a shell, mainly what we're about is running other programs. So this difference of purpose is what explains the reasoning behind the syntax for the most basic kind of command, what I call a process command. A process command is written by specifying the name of a program, and then after one or more spaces, we then put a list of arguments. And the arguments, as we'll see, are not separated by commas, they're just separated by spaces. So for example, a process command might read ls space -la space bin. And what this is first the program name ls, followed by two arguments, the first -la, the second bin. What's going on with these arguments we'll talk about in a moment, but looking first at the program name, if this is the name of some program, some executable file somewhere on the system, how does the shell know where to find it? Well, actually there are three different cases. When you see a program name with no slashes in it, then the shell will search for an executable file of that name in one of the directories listed in what's called the path. The path is simply an environment variable in the shell process. So for example, this is what the path variable looks like in the shell on my system. It has a list of directories separated by colons. First /user/local/sbin, then /user/local/bin, then /user/sbin, and /user/bin, and /sbin, and /bin. Those are all the directories that are in my path. So in my shell, when I run the command foo, the shell will first look for a executable called foo in each one of these directories, starting with the one that's listed first and going left to right. And it goes with the first match that it finds. Assuming it doesn't find any match, then the shell reports an error, saying there's no such program called foo. So that's the first case, when I don't have any slashes in the name of the program. When the name starts with a slash, then the shell interprets this as an absolute path to an executable file. So in this case, /bin/foo, the shell will look for that file. And if there isn't actually a program of that name, then the shell reports the error saying, hey, there is no such program as /bin/foo. The last possibility is that there's a slash in the name, but not at the start. This is interpreted by the shell as a relative path name. So it will look for that path relative from the process working directory, the current working directory of the shell itself. And this is one reason why the shell will display the current working directory, because it's something you often need to know. So for example, assuming that the process working directory of the shell is currently my home directory /home/Brian, this will look for the file /home/Brian/bin/foo. And of course, if there is no such executable file, then the shell will give you an error message. One thing that almost always trips up newbies is they expect the shell to, when they type say foo, to look for foo in the current working directory rather than just in the directories of the path. But this is not the case. As just explained, the shell only looks in the current working directory when there is a slash somewhere in the middle of the name. The trick then to run foo in the current working directory is not to write just foo, but to write ./foo. What's going on here is that in a Unix system, every directory always contains an entry called dot, which refers to that directory itself. This is a special entry that's added to every directory that we create. So when we write ./foo, that's a relative path that's equivalent to just foo. It's just in this case we've now tricked the shell to looking in the process working directory, whereas before it would only look in the path. While we're at it, I'll mention that Unix directories also always contain a directory entry called .dot, which resolves to the containing directory. So for example, a path that reads /home/Brian/dot, that actually resolves to the same thing as /home. Like the dot entry, the dot entry in every directory is sometimes useful when we write relative path names. In any case, getting back to our example process command that begins ls, you can see that the program name here has no slashes in it, so the shell is going to look for this in the path. The motivation behind the path mechanism is that there are a number of programs on any Unix system that we want the convenience of being able to run without having to switch into their directories or having to write out their full path names. So we place these programs in a number of standard directories like say /bin or /sbin, or alternatively we add the directory in which they are contained to our path. That way we can execute them without having to write out their full names. In this case, ls is a standard Unix program, sometimes called the list program, because what it does is it lists the contents of a directory. It prints out on your terminal, prints out the contents of some directory. And on most Unix systems, ls is going to be found in the /bin directory, because /bin is a standard directory for general programs, general common programs. The /sbin directory is so named because it's for programs with super user privileges, hence S. and so you place in there programs which do things that have to do with system administration generally. As for these other directories in the path, these /user directories, we'll talk more about the standard directory layout in Unix systems in a supplement or possibly in a later unit. In any case, that explains how a shell locates a program. But what about these arguments, and how exactly does the shell then execute the program? Well, anytime in Unix you have a program executing another program, what that's going to involve is first a fork system call, and then the child process that gets created invokes exec to actually load that program and run it. So first off, the shell invokes the fork system call, and then after the fork, the parent process invokes the wait system call to wait for the child process to complete. The child process, meanwhile, then has to call exec to actually run the ls program, because until it calls exec, that forked off child, remember, is just a continuation of the shell. It's running the shell code until it actually calls exec. And in this exec call, one of the arguments, of course, is the path to the ls executable file, but then also there's another argument to exec whereby we can pass in what are called the program arguments. In this case, it's two strings, the first reading -la, the second a string reading bin. We haven't previously discussed program arguments, so again, looking at our model of the memory layout of a process, what the exec system call does is it copies the program arguments to somewhere in the heap of the process, and then in the first stack frame, it places the address pointing to these arguments on the heap. And also on the stack, exec places a count of the number of arguments. You might think it should leave an indicator of the size of the arguments, but it doesn't have to, because these arguments always are terminated by a null byte. So as long as the program gets an address pointing to the start of the arguments and a count of how many there are, the program can correctly read all of the arguments passed to it. So now, when we create an executable to run on a Unix system, we are expected to observe the convention that the stack frame is going to contain the address of arguments somewhere on the heap and also a count of the number of arguments. So, for example, when the Python interpreter runs on Unix, one of the first things it does is it looks for the address and the argument count on the stack, and then goes and finds the arguments and puts them into a Python list. And the way you actually access these arguments in a Python program is first you import the sys module, and then in the sys module there's a member called .argv, which v here standing for vector, meaning essentially list. So sys.argv is the list of arguments, here expressed as Python strings. And while it is the case that program arguments could be pretty much any kind of data you want, either text data or binary data or whatever, we conventionally just think of them as ASCII strings. So when we invoked ls with two arguments, the first argument was an ASCII string reading -la, and the second was an ASCII string reading bin. Finally, last thing to say about program arguments is that what they mean is entirely up to the program to which we pass them. In this particular case, ls interprets -la as an option of how to display the contents of the directory, and the second argument here, bin, that's interpreted as the name of the directory whose contents we wish to list. Nothing about the shell, however, governs this. It's entirely up to the ls program itself how it wishes to interpret its arguments. So I have to actually go and read the manual for the ls program. As you'll see, most command line programs on Unix follow a number of conventions in how to pass arguments to them. For example, the usual convention is that arguments beginning with a hyphen specify some kind of option. They're usually called flags. So -la here is a flag to the ls program specifying some option. But again, that's just a convention, so really you have to just break down and read the manual for any program you wish to use on the command line. In bash syntax, certain characters are given special meaning, and eventually we'll enumerate all of these special meanings. In some contexts, you'll want to disable the special meaning so that a special character doesn't signify something special, it just signifies itself. And for this purpose, we do what's called quoting. First off, to quote a single character, you simply precede it with a single backslash, and that character combination, a backslash followed by a special character, simply designates the special character itself without any special meaning. Alternatively, you can use a pair of single quote marks, which will quote every character enclosed within. So effectively, every character between single quote marks signifies simply itself. Similarly, you can use double quote marks to quote characters, except they do not quote any enclosed dollar signs, backticks, backslashes, exclamation marks, asterisks, or @ signs. To understand how you might use quoting, consider the ls command we saw previously. In the top example here, when we precede the space with a backslash, we are removing the special meaning that space normally has, which is to separate arguments. So effectively now what this command will do is we're invoking the ls program, but now we're only passing to it one argument, a string that reads -la space bin. In the second example here, when we enclose the arguments in a pair of single quotes, that backslash now no longer has a special meaning. So this is invoking the ls program with a single argument that reads -la backslash space bin. In the third example here, the backslash is now preceding a new line character, thereby robbing the new line of its normal significance, which is to denote the end of the command. So effectively what we've done is actually split this command from one line into two. So you'll actually see this trick a lot in shell scripts. You'll see lines that have been split from one line onto multiple lines by simply ending all of them with a backslash. In the fourth example, a backslash is preceding the dollar sign, so the dollar sign, which normally is a meta character, has now been quoted and therefore has no special significance. The backslash and dollar sign together signify a single dollar sign character, which is not given special treatment by the shell. It's simply passed as part of the argument to foo. In this last example, however, we're using double quote marks, and inside double quote marks, the dollar sign is one of the special exceptions. It's one of the special characters which retains its special meaning, so it's still a meta character here. What significance exactly the dollar sign has is something we'll get to later.